Hello, in today's video, I'll be solving questions on A-level reaction kinetics from May-June 2023, paper 4-1. Question 3, A. Aqueous acidified iodate 5 ions, IO3 minus, react with iodide ions as shown. IO3 minus plus 6H plus 5I minus giving 3I2 plus 3H2. The initial rate of this reaction is investigated. Table 3.1 shows the results obtained. The rate equation for this reaction is rate is equal to K, which is the rate constant, times the concentration of IO3 minus times the concentration of H plus squared times the concentration of I minus squared. I. Explain what is meant by order of reaction. In this rate equation, the order of reaction with respect to IO3 minus is 1. The order with respect to the H plus ion concentration is 2. And the order of reaction with respect to the I minus concentration is 2. These values are the powers to which the concentrations of these reactants are raised to in this rate equation. So we can define the order of reaction as the power to which the concentration of a reactant is raised in the rate law equation. Complete table 3.2. So we are supposed to complete this table with the order of reaction with respect to the reactant. The order of reaction with respect to IO3 minus is 1. So we put 1 here. That of H plus is 2. And that of I minus is 2. The overall order of reaction is gotten by adding all the orders together. So that would be 5. I. Use your answer to AII to sketch lines in figure 3.1 to show the relationship between the initial rate and the concentrations of IO3 minus and I minus. From the rate equation, we saw that the rate is directly proportional to the concentration of IO3 minus. It means that when the concentration of IO3 minus is increasing, the rate will also increase proportionally. So the relationship is going to be a straight line. When we come to the rates and the concentration of I minus, we realize that the order with respect to I minus is 2. So it is a second order. So it means that when the concentration of I minus is increased, the rate is going to be an exponential increase, which means that the rate is going to be times 2 of any increase in the concentration of I minus. And so the curve to show the relationship is this, which means an exponential increase in the rate as concentration also increases. This is a first order graph of rate plotted against concentration, and this graph is a second order graph for rate plotted against concentration. IV. Use data from table 3.1 to calculate the rate constant K for this reaction. Include the unit of K. The rate equation given in the question is rate is equal to K times the concentration of IO3 minus first order times the concentration of H plus squared times the concentration of I minus squared. So it is second order with respect to H plus and I minus. So we are trying to find K, so we make K the subject. And so K is equal to the rate divided by the concentration of IO3 minus times the concentration of H plus squared times the concentration of I minus squared. From table 3.1, experiment 1 gives us value for the rate and the concentrations of all the reactants. So we can use the values in experiment 1 to calculate the rate constant. So K is equal to the rate in experiment 1 is 4.20 times 10 exponent negative 2 divided by concentration of IO3 minus is 0.04 times the concentration of H plus which is 0.015 squared times the concentration of I minus, which is 0.025 squared. And so when you solve, you get K to be 7.47 times 10 exponent 6. For the unit, we saw that the unit of rate is mole per decimeter cube per minute from the table, divided by concentration of iO3 minus, the unit is mole per decimeter cube, times the concentration of H plus, the unit is mole per decimeter cube exponent 2, times that of I minus is mole per decimeter cube exponent 2. So it means that we get mole decimeter minus 3 per minute divided by mole decimeter minus 3 times this one gives us mole squared decimeter minus 6 times this one also gives us mole squared decimeter minus 6. So it means we get mole decimeter minus 3 per minute divided by, when you multiply this mole, this mole, this mole, it means that you are going to get mole exponent 3. That should be exponent 5 rather, because we have mole here, mole squared, and mole squared. So it should be exponent 5. So mole exponent 5 decimeter minus 15, because that will be minus 3 plus minus 6 plus minus 6. So that should give us minus 15. This gives us mole exponent 1 minus 5 decimeter minus 3 minus negative 15 per minute. And so it means that our unit is mole exponent negative 4 decimeter exponent 12 per minute. Then use data from table 3.1 to calculate the concentration of hydrogen ions H plus concentration in experiment 2. Again, our rate equation is rate constant times concentration of iO3 minus times the H plus concentration exponent 2 times I minus concentration exponent 2. To find the H plus ion concentration, we need to make this the subject. And so it means that our H plus squared is equal to the rate divided by K times the concentration of iO3 minus times the I minus concentration squared. We can find the square root of both sides in order to find H plus ion concentration. And so it means that our H plus ion concentration is equal to the square root of the rate divided by the rate constant times concentration of iO3 minus times the concentration of I minus squared. In experiment 2, we know our rate, we know the concentration of I minus, we know the concentration of iO3 minus. We don't know the concentration of H plus, and that's what we are trying to calculate for. We have also solved for K in this part of the question, and so we can just substitute and find our H plus ion concentration. So H plus is equal to the square root of the rate, which is 4.20 times 10 exponent negative 2 divided by the K, which is 7.47 times 10 exponent 6 times the concentration of iO3 minus which is 0.04 times the concentration of I minus squared, which is 0.025 squared. So we get 2.25 times 10 exponent negative 2 mole per decimeter cube. VI. This reaction is repeated in two separate experiments. The experiments are carried out at the same temperature and with the same concentrations of I minus and IO3 minus. One experiment takes place at pH 1.0 and the other experiment takes place at pH 2.0. Calculate the value of rate at pH 1.0 divided by rate at pH 2.0. Our rate equation was already given as this, but we need to divide the rate at pH 1.0 by the rate at pH 2.0, and that will be equal to the K, which is the rate constant, times the concentration of IO3 minus times the H plus ion concentration that we get when we use pH 1.0 times the I minus concentration divided by the rate constant times the concentration of IO3 minus times the concentration we are going to calculate for when we use pH of 2.0 for H plus times the I minus concentration. From this question, we're told that the concentration of I minus and IO3 minus are the same. So it means that in the two experiments, this is the same as this. This is also the same as this, so we can cancel them out. Of course, the rate constant is the same for both experiments. We have calculated this and it's the same. It means that our value is actually going to be equal to the concentration of H plus squared over the concentration of H plus squared. This will be the concentration of H plus squared at pH 1.0, and this will be the concentration of H plus squared, concentration of H plus at pH 2.0. We know that pH is equal to negative log of H plus ion concentration. For pH of 1.0, it means that our H plus ion concentration is going to be 10 exponent negative 1.0, and this is equal to 0.1. So it means that we have 0.1 squared, and then let's find the concentration of H plus at pH 2.0. Come and put it here and solve for the value. To do that, again, pH is equal to negative log H plus ion concentration. So our pH is 2.0, which is equal to negative log H plus ion concentration. So we divide through with negative 1. It means we get negative 2.0 is equal to log concentration of H plus. If we find the anti-log of both sides, we are going to get 10 exponent negative 2.0 is equal to the concentration of H plus ion. And so concentration of H plus ion at pH 2.0 is equal to 0.01. So if we put that value over here, 0.01 squared, it means that this value is going to give us 100. B. In aqueous solution, ion 3 ions react with iodide ions as shown. 2 Fe3 plus 2 I minus, giving 2 Fe2 plus I2. The initial rate of reaction is first order with respect to Fe3 plus and second order with respect to I minus. The mechanism for this reaction has 3 steps. Each step involves only 2 ions reacting together. Suggest equations for the 3 steps of this mechanism. Identify the rate determining step for this reaction. When you have a question like this, the first thing to do is to react the two reacting ions together. And so we have Fa3 plus I minus. And this should give us an intermediate. The intermediate is going to look like Fe3 plus I minus intermediate, but we can't have this. So it means that the Fe3 plus, the Fe and the I are going to join together. So we get FeI. And if you subtract minus 1 minus from 3 plus, we get 2 plus. It means that our intermediate is actually going to be FeI2 plus. Once an intermediate is formed, it is used in the subsequent step. So we have FeI2 plus we need to react this intermediate with I minus because this intermediate actually contains Fe3 plus and I minus. And if you were to react another Fe3 plus, that's the second mole of Fe3 plus with this Fe3 plus and I minus intermediate, it means that we are using 2 moles of Fe3 plus. But we can see that the reaction is first order with respect to Fe3 plus. So it means that there is nowhere we have to see 2 Fe3 plus reacting together. That is not going to happen. So it means that in this second step, we can only use I minus because the reaction is second order with respect to I minus. And notice that there is I minus in this intermediate. And so if you use another I minus, it will mean that we are using 2 moles of I minus and 1 mole of Fe3 plus. And so that will be, and so it means that our second step is going to give us the rate determining step. So we have to react the intermediate with I minus. And if you do this, we get Fe2 plus I minus, but we have added another iodine. You can see that the 2 plus from here was maintained on the Fe, and then the iodine is going away to add onto this. So it means that it is just going as I. So it means that this will just be I2, but with a negative charge on this because the negative charge was already on this. From the 2 reaction steps so far, we have used only 1 mole of Fe3 plus, and we have used all the 2 moles of I minus, and we have formed only 1 mole of Fe2 plus. It means that we have to use the second mole of this in the next step. And so that is going to be Fe3 plus. Notice that this is an intermediate formed in the second step, and this intermediate must be consumed in the subsequent step. So that will be plus I minus 2I2 minus. And so that is going to give us our second mole of the Fe2 plus, that is Fe2 plus we have not formed I2, so that is going to give us I2. Notice that charges are balanced on both sides of this equation. It is plus 2 on this side. If you add plus 3 to minus 1, you get plus 2. It means charges are balanced. The rate determining step is our second step. So this is step 2, because inside this intermediate, we have 1 mole of Fe3 plus, which corresponds to first order with respect to Fe3 plus. We have 1 mole of I minus in this intermediate and 1 mole of I minus over here. So that will be 2 moles of I minus in this second step, which corresponds to second order with respect to I minus. So our step 2 is the rate determining step. Thank you for watching. See you again in the next tutorial. Please subscribe to this channel.